In this tutorial, I'm going to show you how to establish I2C communication with a DS3231 Real Time Clock, or RTC. Now, the purpose of this tutorial isn't to quickly show you how to get your clock up and running. Instead, I'm going to show you something better: how to read a datasheet such that you are able to use any I2C device and an Arduino. Many tutorials are out there to show you how to talk to a particular device. There are also many Arduino libraries out there to make it easy for you to use a particular device without you having much understanding of how those devices work or what it is that you're doing. The surface level understanding of these guides and tools make it easy for you to get started. This is part of the reason why Arduino is so popular. However, complete reliance on available resources may limit you in your choices and thus what you can do. I have downloaded libraries in the past that are faulty or incomplete. I have followed tutorials that just don't work. Sometimes I have a device and there are no resources like tutorials or libraries for it. If this is the case, you need to know how to solve your problem, and this all starts at the datasheet. Learning how to get started from scratch with a datasheet is what this tutorial covers. So let's get started. To complete this tutorial, you're going to need an Arduino Uno or a different type of Arduino, a cable that brings the Arduino to your computer, a DS3231 breakout board shown here, a breadboard, and some wires to bring it all together. Finally, you're also going to need the datasheet for the DS3231. Check the link in the description if you are needing help finding it. First, let's take a look at the RTC. This breakout board has 7 pins: VCC, INT, SCL, SDA, ground, 32K, and RST. What are these pins? Let's take a look at the datasheet. Surely it will explain. Page 1 is our general description and introduction of the device. It shows us the pinout of the chip. Here we see VCC, INT/SQW, SCL, SDA, ground, 32 kHz, and RST. I think it's safe to say that the breakout board silkscreen matches the nomenclature used in the datasheet. We also see a circuit surrounding the chip here. Any well-designed breakout board will have the correct supporting circuitry around it. You would have to check the schematic of your board to ensure that this is correct. Alright, let's move on. Page 2. We see VCC here has an operating voltage between 2.3 and 5.5 volts maximum. We know that the Arduino is a 5-volt device, so we know that this chip will work fine with our Arduino. Now let's continue moving along until we find what the other shorthands mean. On page 9 of the datasheet, we have a list of all the other pinouts. So starting with the pin 1 here, 32 kHz. So this is a 32 kHz output. And down here in the detailed description, we see that the RTC is driven by a temperature compensated 32 kHz crystal oscillator. We have our VCC, which we know is DC power in. We have our INT/SQW pin. This is our active low interrupt or square wave output. So with these clocks, you can get it such that it pulses at a certain frequency to help you keep time on your device, and you can set that frequency later. RST is our active low reset. If we were to connect a button here, we would be able to reset the clock. I'm not interested in that, so I'll move along. NC is no connection. Ground is ground. And then down here, we have our SDA and SCL lines. This is our serial data input-output and our serial clock line. I2C uses 2 pins to transfer data. One is our clock signal, SCL, and the other is SDA. Great, now we know the pinout of our breakout board. Let's go ahead and connect it to our Arduino. For us to do this, we're going to have to know the pinout of our Arduino, and here I have a handy-dandy pinout. So we're going to connect ground to ground. We're going to connect VCC to 5 volts here. And then for the data lines, we need to connect to SDA and SCL. These happen to be analog 4 and analog 5 respectively. For the interrupt, we're going to connect it to interrupt 0, which is digital 2. If you're not using an Arduino Uno, you're going to have to load up your own pinout and figure out the equivalent interrupt SDA SCL pins. Now let's get programming. Open up an instance of the Arduino IDE. Now, because we're going to be communicating on the I2C bus, we need to include the Arduino's library for I2C communication. That is the wire library. Go to Sketch, Include Library, and then Wire. Now, the way I2C devices work is that each slave device has an address. The master, in this case our Arduino, calls on the slave's address and then sends data. We need to know the address of the DS3231. The datasheet should tell us what this is, and in fact, if you go down to page 16 on the datasheet, we see the 7-bit address that is 1101,000. Now I try to avoid writing binary for things like this and prefer hexadecimal as it's easier to make a mistake writing in binary. A quick Googling finds us a converter that will convert binary to hexadecimal. So let's type in 110100 and we get the hexadecimal value of 68. Let's write this down in our sketch so we don't forget it. So we're going to define our DS3231 address as 0x68. Now you might think 7-bit address? A byte is 8 bits. What's going on here? Well, we can see from the datasheet that the 8th bit in the byte is being used as a read-write control bit. So we're contacting the address and then telling the device whether we're going to read or write to it. This is like two different addresses. Fortunately, the Arduino wire library that we imported makes it easy for us and takes care of that 8th bit, as this is standard for I2C communication. We only need to worry about the 7-bit address. The DS3231 offers a lot of functionality. To keep this tutorial short, I'm going to focus on writing code to accomplish 3 things. First, I want to figure out how to set the time of the clock. Second, I want to figure out how to read the time of the clock. And finally, third, I want to set the interrupt frequency of the clock on the interrupt pin. So let's start with requirement 1, setting the time of the clock. On the datasheet, go to page 11. Here you have the timekeeping registers. So the way I2C communication works is first you contact the address and then you send to that address the register you want to talk to, and then you send the data that is relevant to that register. So in the case of the DS3231, if we wanted to set the seconds value of the clock, first we must contact the address hexadecimal 68 and then the register hexadecimal 00, and then we can send it the data that we want to set. On this page, we can see that we can send the following time values to the clock. We can send seconds, minutes, hours, day, date, month, and year. So in our Arduino sketch, let's do 2 things. Record the address of the register and create a structure to hold the time values. Structures make keeping track of data easier. So first, let's start with, we're going to define the DS3231 seconds register. And we know that that is hex 00. Then we're going to create a structure, and I'm going to call it time parameters. So we're going to have our seconds, we're going to have our minutes, we're going to have our hours, we have our day of the week, we're going to have our date, we have our month, and finally we have our year, and this matches the same order on the datasheet. Let's give this a save. Going back to our datasheet, we see that the structure of our time data in our timekeeping register is in a binary coded decimal format. So for example, in seconds here, we see that bits 4 through 6 represent the 10-second indicator, and we see bits 0 through 3 count the individual seconds. This means that in our sketch, we're going to need a way to translate our binary coded decimal down to decimal that we would easily be able to type in. And to do that, we're going to have to create 2 functions. So let's go ahead and do that now. So first, I'm going to prototype these 2 functions. So static uint8, and I'm going to call the first one convert value in. So this is when we are receiving data in from the clock. So we're going to pass in the value. And the second function is going to have the same output, and we're going to convert the value out. So that's when we want to send value out to the clock. Okay, so let's create these functions now. I'm going to put them right before our setup function here. And we're going to start with convert value in. And into that, I said we were going to pass an 8-bit integer called value. Let's include brackets here. And so what we're going to do is we're going to create a value called converted val, and it's going to be equal to our value in minus 6 times the value that we received in shifted over 4 places. Now, you might look at that and go, where did you get that, Zan? And I'm going to tell you it took a bit of figuring it out. I'm not going to spend time explaining how that works in this tutorial. I mean, you can do the math there and you can determine whether or not it's going to work, but we're going to do the same thing again, for our converted values out. And in this case, we're going to create again a converted val that we send out, and it's going to be equal to our value in. We're just going to reverse the operation. We're going to add 6, and then we're going to multiply it by our value divided by 10, and then we will return out our converted val. Okay, so now we're ready to start writing a function for setting the time of the clock. Let's do that now. So I'm going to call this function setTime, and into it we're going to receive our structure, that is time parameters, and it's going to be in this format. We're going to call it time valves in the function itself. And just so that everybody's on the same page, I'm just going to write down from the datasheet. We know that our 0th entry is seconds. We know our first entry is minutes. In fact, here, if I just move this over, we can see this here. So seconds, minutes. We know our second entry is hours. Our third is day. Our fourth is day. Our fifth is month. And finally, our sixth is our year. So the first thing we're going to want to do is begin a transmission with the device. So we use a function built in called begin transmission, and we want to then type in the address of the device. So because we already defined it, it's nice and easy for us. We then want to tell it what register we want to talk to, and I called that register DS3231 seconds reg. So now we have the address, and now we're telling it what register we want to write to, and then we send our data over to the chip in the order that the chip expects it. So we're going to write, and what are we going to write to the chip? We're going to write our converted value out of our time vals pointed to the second value. And then we're going to do this again for our minute. So time vals pointing to our minutes. We're going to write out our time vals for the hour. And we continue for the rest of our time values, except for day here. So I'm going to say, because I don't care about the day of the week, I'm going to just write a 0 there. But otherwise we continue this for the rest of our values. So once we have told it to write these values out, the next thing we need to do is end the transmission. When you do this, this is when it actually goes through and does everything that you're expecting it to. And then we will just add a 5 millisecond delay here on the end so that, you know, things have time to actually complete. So that's all we need to do to set the time. Like it's just that simple. So we say contact the address, contact the register, send in the values that we want, end the transmission, boom, done. So that's requirement 1 done. Let's now work on requirement 2, which is read the time from the clock. So we're going to create a new function here, and this function is going to be called read time. And into this function, we're going to pass in time parameters structure again, called time vals. And let's go ahead and get this going. So similar to before, we need to begin a transmission with an address. So we're going to begin our transmission with our DS3231 address. And then we need to write to the registry that we want to read from. So we're going to say DS3231. What did I call it? I called it seconds reg. And then we are going to end the transmission. And this way, we know that that's the registry that we have last contacted on the chip. So now we can make a request from the DS3231 address. We're going to request out of it a byte type, size of time parameters. So now we're telling the chip, okay, hey chip, I want to talk to this registry. Finish. Now when we go and we contact the chip again with a request, we contact the address and we say, hey, we're going to request from the last address, last registry that we contacted, which was our seconds registry, and we're going to request out of it all of the data in our time parameters here. So now we can write to our time values structure, and we could say that our seconds are equal to convert the value in. and we're going to not write this time, but read. We're going to have to do this with every value. Now again, because we didn't care about the day of the week, that's just going to be a read. We're not saving it anywhere, but otherwise we're going to have to continue along. And then at the end, we will just add, again, a 5 millisecond delay here. So there we have it. Now we have met the second requirement that we've listed out before, reading the time from the clock. So the last thing we need to do is set the interrupt pulse rate, or the SQW frequency. So how do we do this? Well, if we take a look at the datasheet's page 13, we see that we get the information relevant to the control register. And in here, we see this bit 2 is our int cin. And if we read about this, we see that this is the bit that controls the int/SQW signal. When the int cin bit is set to logic 0, a square wave is output on the pin. So this means we need to set this to 0. We also see right above it that we have a square wave output frequency, 1 Hertz, 1000 Hertz, 4000 Hertz, and approximately 8000 Hertz. And this is done by changing the rate select RS2, RS1 pins. So these bits control the frequency of the square wave output when the square wave has been enabled. So really, here in this control register, we want to adjust bits 2, 3, 4, as these are the ones relevant to getting that square wave output. The rest of these bits do other things. And I mean, the datasheet's right here in front of us, so I could go through what those other things are, but I'll let you do that on your own time. Instead, what I'm going to advise is when we start changing this register, we don't change these other bits that are irrelevant to us, because we risk doing something with the device that we don't want to do. So we're going to leave those unchanged, and instead we'll just change bits 2 through 4. So let's start this by recording the control register address, which in this case is hex E here. So up at the top here of our sketch, we're going to define our DS3231 control register. And we know that this is 0x0E. Down here, we're going to create a new function. This function is going to be called setIntFrec, or frequency. And into this function, we're going to pass our frec option. So just so that we're all kept in the same loop here, option 1 is 1 Hertz, option 2 is 1024 Hertz, or I should just say 1.024 kilohertz. So let's go ahead and get this started. So the first thing we're going to want to do is begin our transmission just like before, and we're beginning it with our DS3231, so we type in the address of this. Then we need to tell the chip what register we want to talk to, so we're going to write to our DS3231 control register. We're then going to end the transmission. Now this is starting to look a lot like what I did before when we read the time from the clock. Why am I doing this? Is because we're going to want to read out what this control register is before we change it. That way we can only change what we want to change, because right now I can't tell you what it's set to. I mean, who knows what was programmed on this clock before. So what we're going to do is we're going to request from our DS3231 address. We're going to request one piece of data, 1 byte, and we're going to create a value here called current config, which is going to be equal to reading the device. So now we've read out from the clock what our current configuration is. So now we can go ahead and start changing it. Well, we have a few options here, so let's create an if statement that says if our frequency option is equal to 5, means that we want to shut it off. So we're going to say byte off config, byte off config is equal to current config, which is what we're currently getting in, or, and then we're going to say or bit 2. So everything else is going to be 0 here, and 0 here, and then a 1 here, because if we set this to 1, then we set the square wave functionality off. So we're going to type it in, 5 zeros, a 1, and then 2 more zeros. So we have a bitwise operator OR here. What this means is it's going to compare the value current config and this binary value I just typed in, and if any of the values are 1, so either or are 1, then set it to 1. If we set that value to 1, our int cn is off. So now we need to send this configuration back to the clock. So we're going to begin a transmission. We're going to talk to the 3231. We're going to now want to write to the DS3231 control register. And then we're going to write our off configuration that we just created. And then we will end the transmission. So effectively, we just upload our off configuration to it. Done. So great. Next, we're going to have to compare if the frequency option is anything else that is relevant, so less than or equal to 4. Sorry, I should say if it's less than 5. And then what we're going to do here is create a new value called option. So I mean, here we have option 0, option 1 on the datasheet, 2 and 3, and we don't have a 4 here, so we gotta take our option and just subtract from it 1. So our option is going to be what we inputted, and we're going to subtract 1 from it. We're going to want to create a new configuration value that we want to send out, and it's going to be equal to our current config, which we have already read in, and then we're going to use bitwise operator AND here, and we're going to set bits 3 and 4 to be 0. So what we're effectively doing here is wiping those 2 bits, because that's what the AND does, is that it's going to stay 1 if the bits in here are 1. Also, if we're going to want to be able to get our square wave input, we're going to have to set bit 2 to be 0 as well. So let's do that. These 2 lines of code could be written on the same line, but I'm separating them here for clarity. In this case, we're going to be making it such that the second bit is low. Now we need to write our option that we have here. So this is our option, which is going to be 0 through 3 as defined on the datasheet, and we're going to have to set this to be our new configuration that we want. So we're going to say our new config is equal to new config, and then use the bitwise operator OR to say we're going to shift our option over 3 places such that we can write it to bits 3 and 4 in this byte. Now that we know what our new configuration is going to be finally, we can send it over to the clock. So we're going to begin transmission again. We're going to talk to the address of the chip. We're going to write to the DS3231 control register. We're going to write our new config. And then finally, we're going to end transmission. When that's all done, we're just going to add a 5 millisecond delay here at the end. So there you have it. Those are all the functions that we're going to need to be able to complete these 3 requirements. So the rest of the sketch is just going to be your standard Arduino sketch. Everything, I have 123 lines here. So everything in these 123 lines, more or less, could be put into a library. And that's effectively what a library is when you download it to work with one of these devices. In our sketch here is where we put the meat of what we want our program to do. And what we're going to do is first we're going to create a value called time trigs. So remember, we're going to get a square wave output, and this is going to flip our interrupt, and this is going to be our interrupt counter, effectively. So if we're going to have an interrupt counter, we know from a previous tutorial that we're going to need a function that the interrupt points to, and in this function we're just going to increment our time triggers by 1. We're then going to prototype a time parameter structure that I'm just going to call foo here so that we can read our values and save to it. And then we're going to go into our void setup function here. And the first thing we're going to do is establish serial communication with a baud rate of 9600 between the computer and the Arduino. We're then going to begin an instance of wire communication. So this starts the I2C communication, and I'm just going to give it a couple of seconds to stabilize itself. And then I'm going to create a time parameter structure here called example values. And I mean, you can rename this however you want. You can create it however you want. And really what this is going to be is, let me just fill this out. This is just some dummy seconds, minutes, hours, day, and then we had our date, our month, and our year. So you see that this is very close to December 31st of 2010 that I'm writing here. And we finish that off. And then the other thing we're going to have to do is set the interrupt frequency that we want. So I'm going to say that I want my desired frequency to be equal to option 4, which I know is the 8192 Hertz option. And then we're going to set the time using our set time function. We're going to send over to it our example values. So this sets the time. We're then going to set the interrupt frequency using our handy dandy setIntFrec function, and we're going to send over to it desired frequency. And then we're going to attach an interrupt to interrupt 0. We're going to point it to our time function when we detect a rising edge. Okay, so now we can go down to our loop. First thing we're going to do is give it a second. Just going to wait. We're then going to read the time out of the clock, and we're going to write the values to our foo time parameter structure. And then we're just going to print out what the time is. So first we're going to start with foo.y for our year. We're going to say this is our year. We're going to print foo.m for month, and we're going to do this similar for every other date-like value. And then at the end here for the date, we're just going to have date. So that will be one line of text, and we're going to do the same thing for our hours, our minutes, and our seconds, with a print line on our second statement here. So the last thing we're going to do is we will say we will print trigger count so that we know that our triggers are happening on our clock, on our square wave output, and we will finish that off with time trigs. And then right at the end, we'll just have a if time trigs is greater than or equal to 8192, then we reset time trigs to 0. So let's verify this. I'm sure there's going to be a typo somewhere. Be sure to include semicolons at the end of all of your lines of code. So let's go ahead and give this an upload to our Arduino. When that's done, open up an instance of your serial monitor. And here we see it. There's our date with our time, and we see that our time every second is incrementing by 1 second. And Happy New Year! It is now 2011, January 1st, 3 seconds in. So whenever you change these example vals in our sketch, it will change what those start times are. And here we have our trigger count, which is how many triggers are actually happening from the real-time clock per iteration of the loop. We know that we are delaying for in our loop here for 1 second at the beginning. We then read from the chip, we print some stuff out, and then we print how many time triggers have happened, and we see that this value is always over 8,192, which makes sense because it takes time to do all of this stuff, so we know that that's working appropriately. So there you have it, how to read a datasheet for an I2C device, connect that device to your Arduino Uno, program the device, and use the device for something functional. I hope you enjoyed this tutorial. For more tutorials like this, visit thezanshow.com.